welcome everyone for this new session. So after having a full session for Postgres internals, we have the chance to have another Postgres internals with Divya Sharma from AWS, fantastic Postgres enthusiast helping customers from AWS succeed with Postgres on AWS, and she will tell us everything we need to know about MultiXact and Postgres. Thank you.
Thank you so much. Thank you very much. I'm audible, I believe, because this is a loud mic. So today we'll be talking about MultiXacts. I think I don't need to introduce myself a little more. This is already done, but I am a Postgres database engineer with AWS, and I've been working with AWS for the past 8 years now, or a little more. And yes, I do help customers optimize their workloads on RDS and Aurora Postgres. So even if you have any general questions about that later on, I will be happy to answer. But today, the topic of interest is MultiXacts in Postgres. This is an oddly shaped stage a little bit, so I have to be up and down a little bit more to cater to the audience, but feel free to ask any questions in between. I would be happy to take those. So how many of you are actually users of RDS or Aurora Postgres? Right. And how many of you have actually seen this metric or this graph on maximum use transaction IDs? If you don't have an alarm on it, before we even start this, please have an alarm on this metric. Why? Because of the transaction ID wraparound. So Postgres has a limited number of transactions which your system can run out of, and it is absolutely necessary for you to have an alarm on this metric to know how much is left, how much you can go before you wrap around. So that's the first key takeaway from today. So, you know this graph, this is what it shows, the max use transaction IDs, the normal transaction IDs. When auto vacuum freeze max age reaches, when the transactions utilized reach this threshold, auto vacuum will trigger to freeze transaction IDs so that you don't get into a wraparound, right? And in this graph, it only depicts standard, normal transaction IDs. So assigned to individual transactions performing write operations, and each transaction has one XID used in the tuple headers. But what if there are multiple transactions locking the same row concurrently? And for that, we need something called MultiXacts in Postgres. So before we understand that, let's look at how a tuple header looks like. This is a row in Postgres, and you have multiple things. You have the CTID, which basically tells you where is this row in the page. Then you have the XMIN, which is the XID of the transaction which created this row, which inserted this row. Xmax, with the transaction ID which basically made this row obsolete, so deleted or updated, and then CMIN, CMAX, Informa. So there is a lot of information in the tuple header, right? And however, Xmin and Xmax is a single value. You can't store more than one value there. So if multiple transactions are trying to access the same row, there is no space. I can't store it there. So what we do is we create something called a MultiXact structure. So this is how it looks like. And when in this example, the multiple transactions which are T1, T2, and T3 are trying to access or lock the same row, they are called as MultiXact members, and there is one ID, 1, 2, 3, 4, which is stored in the Xmax. So this is that MultiXact ID, and these are the members. And the members, as you can see, have a transaction ID and the state, the MultiXact status as to what lock is it taking, right? The info mask also stores some information about if if this is logged by multiple transactions, in the heap xmax is multi. So that flag will be true if this is a multi-exact. So there is an extension in Postgres called PG row logs, where basically you can see that if I do that for PG accounts, for this example, I had multiple transactions open for the same set of rows. You will see that the logger there, you will see the multi-exact ID. You see multi is true, which means it is logged by multiple transactions. You see the transaction IDs and the status. So it was a select for share, both the transactions. That's why you see the mode as share. So this is how you can see that, okay, these are logged by multiple transactions. Operations which use multi-exacts, foreign keys and multi-exact. So basically, whenever you are accessing rows in the child table, it will, and if it is referencing some rows from the parent table, it will log those rows in the parent table, and that will, concurrent access will use multi-exacts. Select for share is exactly what is used by the foreign keys, and that's how you will have the multi-exacts. Sub-transactions, because sub-transaction, you can have multiple transactions within a couple of in a transaction, or by using save points, which creates explicit save points, that will also create multi-exacts. And the fourth one is some drivers or abstraction layers, like for example, the JDBC autosave option. There is an option in that which will, and the name of the option is always. If the autosave is set to always for the JDBC driver, it sets a save point before each query and rolls back to that save point in case of failure. So those save points would actually internally create multi-exacts as well. So this is an example just to show that, okay, if you have a table for songs and a table for users and a streaming table, and let's say, for example, the streaming table, by the way, has two foreign keys from the song and the user table. And let's say, for example, a new song is released, right? So people will start streaming that song and will start using the streaming table. Now, you get a key share lock on the remote table if you insert or delete a row on the table with a foreign key constraint. So because the streaming table has foreign keys from song and user, you will see logs on the parent tables. And those logs will be key share logs. So that lock will prevent modification on the keys in the remote table, in the song and the user table. But that's when you would also see multi-exacts. Any questions till now? I would be happy to take questions in between. Right. I hope it's clear then, because I will assume it's clear. So let's talk about multi-exact storage, wraparound, and vacuuming. And I will try to compare this with standard transaction IDs. So if you have a good understanding of standard transaction IDs, you will be able to compare it with that. If not, please ask questions in between. So the multi-exact information, as you saw, those arrays are stored in the PG multi-exact subdirectory, which is in the data directory in Postgres. And it has two subdirectories. One is the offset, and one is the member subdirectory. So offsets stores the starting offset for each multi-exact member. So you see the ID, the one ID which we saw, which was in the Xmax, that was the multi-exact offset. And the members is the array which is of the transaction ID and the status flag. So that there down below is the ID, and then the members, the transaction IDs and the status of the transaction. It needs to be stored to disk, but it is also cached in memory for performance in SLRUs, and I will explain that in just a minute. But this is the basic storage for multi-exacts. And by the way, PG exact is for the standard transaction ID. So this is for PG MultiXact, which is for MultiXacts, and PG exact. PG exact is for standard transaction IDs, the storage, right? So this is how it looks like when it's stored, and the status is important, right? Because you need to know the status to check how these transaction IDs are accessing the data. Just like standard transaction IDs, MultiXacts are also a 32-bit counter. So, and they require wraparound management as well. Because again, whatever it is an integer limit. You still have a limit of transaction IDs you can do. There will be no new transaction IDs, multi-transaction IDs generated once there are fewer than 3 million left under the wraparound. So as soon as you reach 2.1 billion, or if the space occupied by MultiXacts is roughly around 20 GB. So in standard transaction IDs, we just have the first clause that if we reach 2.1 billion transaction IDs, we can't do anything. But for MultiXacts, there are two clauses rather than one. It is also restricted with the size of the directory, which can go to approximately 20 GBs. So this is one main difference. Wraparounds can happen for both normal transaction IDs and MultiXacts independently. So this is one main thing to note, another key takeaway from today, because well, at least for RDS and Aurora Postgres, you have a metric to show that the metric I showed in the beginning. That is for standard transaction IDs. So you can put alarms on it. It's easier to monitor. But for MultiXacts, the problem is because at least by default, we don't have a metric in RDS and Aurora Postgres. It's harder to track. So, but the wraparounds can happen for both. So if you see and this is what you will see in the error log, that MultiXact members limit has exceeded and you can't create more MultiXact members, but the remaining, because there is no remaining space. So that is an indication that you are using MultiXacts, and you should look into what operations are using those. So like standard auto vacuum for standard transaction IDs, auto vacuum also works to prevent MultiXact wraparound. And how does it work? So, you know the auto vacuum freeze max age, right? Which I showed in the beginning as well. Auto vacuum freeze max age is by default set to 200 million, and it is for standard transaction IDs. For MultiXacts, auto vacuum MultiXact freeze max age is set to 400 million, which means auto vacuum will trigger as soon as you have consumed 400 million MultiX IDs, and it will trigger an aggressive vacuum to freeze those. Okay, so it's a similar concept. The threshold is different and the value is different as well. It's 400 million rather than 200 million. But as I said earlier, it is also space dependent. So obviously auto vacuum also had to trigger aggressively on the space parameter. So if the amount of disk storage occupied by MultiXact directories crosses an internal threshold of 10 GB, which is half of 20, the threshold which I explained earlier, if it reaches around 10 GB, then aggressive auto vacuum will trigger. So yeah, please.
Why is it also space dependent? Wait.
Why is it space dependent? Yeah, that's fine. Why is it space dependent? That's a good question, because the moment you increase this array, or the moment this space gets bigger and bigger, you will start having performance issues in accessing this data. And that is why it is space dependent. If anybody has a better answer, please, we can have this as a discussion as well. But I think that's why it's space dependent, so that they are relatively smaller and you don't get performance issues. So that is threshold dependent and space dependent. And just like standard auto vacuum, standard transaction IDs, the system will launch auto vacuum processes to prevent wraparound, even if auto vacuum is disabled, even in this case. So basically auto vacuum will work to prevent standard transaction ID wraparound and multi-exact ID wraparounds. You can also run, just like you can run standard vacuum or vacuum freeze for standard transaction IDs, you can also run it for multi-exacts. There is one difference though. I mean, obviously the thresholds would be different, right? So a normal vacuum will only freeze or will not freeze, will only release multi-XIDs older than the vacuum multi-exact freeze manage and remove the corresponding files from PG multi-exact directories. This is also the same for standard vacuum, by the way, for normal XIDs, but the threshold is different. But this is a standard vacuum. The difference between vacuum freeze is that it will release all the XIDs and will also delete the file. So it will also do that operation for all completed XIDs and not just the one which are older than that age. So that is the difference. So if you have a situation where you are seeing a lot of multi-exacts being used and you are seeing the space is growing for that, which I will show how to see later. But if you see that is increasing, then running a vacuum freeze will be beneficial. How do you monitor multi-exact IDs? Because as I said, it's at least for RDS and Aurora, it's easier to monitor standard XIDs because of that metric. But for multi-exacts, we have a couple of ways to track as well. It's not that straightforward, but there are a few ways to track it. First is by just querying the age. So you query to find the highest multi-exact age. You query for the database. So you find the database with the maximum age for that for multi-exacts, and then you query to find a table in that database, that which table is actually having the oldest multi-exact age. If your workload is not generating any multi-exacts, then this value will be 0. You will see your values the values will be 0 for your tables. So querying the database is obviously one way of checking. Second way of checking is, as I already said, if it grows till 20 GB, you won't be able to have any more multi-exacts. So it will start running aggressive vacuum. Auto vacuum will start aggressive vacuums at roughly about 10 GBs, right? For RDS and Aurora, you do have two extensions separately where you can use functions to examine that, okay, you can use the Aurora stat utils extension to examine the storage, the size of the PG multi-exacts. So you can do that for Aurora, and for RDS, you can do the same. There is another function. So it looks something like this. If you have RDS tools extensions installed, only then you can run this query and you can get the size of the multi-exact members. Members and offset, both the directories. Remember, you have to check for both the directories, not only one. So that is one. And this is interesting because PG stat SLRU is a view which was released in Postgres version 13, which shows information about the SLRUs. So basically what it shows is how many, when I was trying to access that data, how many were hit how many were there in the shared buffers already, how many I had to read, how many were written, and how many flushes truncate. So similar to how basically you see the data for, yeah. Yes, go ahead. Sorry, 1 second.
Hello. So this multi-exact is used only for reads, parallel reads, or also writes as well? Is it like?
It's for those operations which I mentioned before, right? So for let's say for example, if you are doing select for share or select for update. So for those operations, it will be used. Yes.
But what about?
So it can be both.
That means for update operations, I can use multi-exact, right?
Select for update. Yeah. Select for update can use multi-exacts, yes.
Select for update, right?
Sorry, one second. These operations explicitly, which I just one moment. You can probably look at this. So this will be update. Sorry. So for key share, for no key update, and for update. These are the operations where it can use multi-exacts,
So
to be
maybe
precise.
one follow-up question. So suppose like one transaction is reading the data, right, from the row, and other transaction is updating the data from the row. So how this actually?
That is what we are trying to stop. So basically, when you do a for share, that means you are doing a select. Okay, so for share means that you are doing a select on a specific number of rows, and those rows can, while you are selecting from that data, that lock is taken so that that data is not modified. So it's not allowing the modification of data, if that is your question. That is what is meant by select for share, right? So if you are if you are doing a simple select, right? I'm doing a simple select, and your data can be modified in your snapshot, correct? Right. But if I'm doing a select for share, that means if I'm reading these set of rows, I will allow another transaction to read these rows, but I will not allow another transaction to modify this data till the time I'm reading these rows. Make sense? Yeah, we can discuss on this later also. Yeah, no problem. If it's explicitly about the operations which can go on this, I can take this later as well. But yeah, basically that's what we are trying to avoid, that we don't want to. Yeah. It's specifically for those operations, but we can discuss that later as well. So yes. So coming back, if we want to monitor and analyze through that, you can also do it through the pgstat slru view, right? And that view, basically it shows that how your slrus are being used, okay? And slrus are just not used for multi-exacts, but that view can show information about multi-exact usage. So both for multi-exact member and multi-exact offset. Well, right now, that output will not tie to any sessions which are using multi-exacts. So you can only confirm that multi-exacts are being used and the rate of usage, but you can't really tie it back to a session at this stage. There is a very good talk by Alvaro in the PGCon DE. That's the link to the talk. And it's on SLRUs. And I just copied 2 slides from that talk because it was really good. And it basically shows how SLRU search has been optimized in Postgres 17. So basically, what we do this is how the scanning and searching in the cache works, right? You scan linearly the array of buffers to see if one contains the page you want, right? Then if we find it, we are done. We are happy if it's there in the cache. If not, scan has chosen a victim buffer to evict because it's not being used, right? So we have selected it to evict, leaving the buffer free, and load our page into the buffer, increment recently used counter using atomic ops, and now use the page in the buffer, right? This is how the cache works. But in 17, for SLRU access, we have optimized the search, not we, I mean, Postgres has optimized the search for SLRU using banks. So, to simply understand it, instead of scan linearly the array of buffers to see what it contains, only scan linearly the buffer of arrays of the bank that contains the page. So basically the SLRU buffers have been divided into banks so that we don't have to linearly search the entire thing. We can just search the small piece of the bank which contains that page we want. And what is the benefit of doing this? So it basically partitions SLRU buffer slots into multiple banks to reduce log contention, because now you don't have to access the entire, log the entire SLRU globally. You can have, instead of having a single global log, you can have separate bank logs. And that you can access different SLRU pages simultaneously if there are different if they are in different banks. And this reduces the log contention, and you can do high concurrency workloads. So that is an optimization added in version 17. Identifying wait events related to MultiXacts. If you see any of these wait events in performance insights, database insights, or any of your monitoring tools, if you see these wait events either in that or in just wait events in the PG stat activity, if you see this there, then that means if it's a top wait event, then you are using MultiXacts, and it's time to figure out where. This is how it looks like in performance insights today. You will see, this is an example of when MultiXact offset buffers was having a lightweight lock, and you can see that it was the most highly weight event visible in the performance insights dashboard. So this is how it can be visible. And just before we get to the best practices to manage MultiXacts, I actually, how much time do I have? How many? 20, wow, okay. So this is the slide I created, which I thought I will only show if I have time. But now that I have time, because it's a very text-heavy slide, but it basically is a slide which compares standard transaction IDs to MultiXacts. And you can see that basically, if you understand the concept of standard transaction IDs, it is easy to compare it like this. So we will go through these now that we have time. The purpose and use case of standard transaction IDs is obviously used for MVCC visibility checks, and each transaction is doing an operation, and each transaction has XID in the tuple headers, right? One XID. Multiple transactions will need multiple XIDs, which we can't store in the tuple header, and that's why we need this MultiXact structure. For the tuple header representation, Xmax contains a single XID, which is locking or updating transactions. And for MultiXacts, the bit is set in InfoMask, and the XID, the Xmax, store the XID of the MultiXact ID. Storage, for standard XIDs, PGExact stores the information of the transactions. For SLRUs, you have two subdirectories which store this information. For wraparounds, both of them wrap around at 2.1 million transactions. But for MultiXacts specifically, you have a separate wraparound for member storage. That is an additional factor. Lifecycle and persistence, you assign to a transaction when it first writes, and on demand when the rows are logged by multiple transactions. This is how it is different. Like, it is slightly different in the tracking parameters. So rel frozen XID, rel min name XID. I mean, just the names are different, but concept largely remains similar. Vacuum behavior also. The vacuum freeze, as it freezes the normal XIDs, will also freeze the MultiXact IDs. So yes, I have covered this. I only kept this if I had time, but great. So now for managing MultiXacts, right? We've discussed what are they, how are they caused, how can you monitor, but how do you manage them? So vacuum freeze is the one which will freeze them at just like standard transaction IDs. And if you see using the queries I provided, if you see that, okay, there are tables, database and then tables which we have identified that which use MultiXacts, then maybe manual vacuuming, manual vacuum freeze nightly or bi-weekly would be recommended. Because for auto vacuum, multi-exact freeze max age is set to 400 million. Aggressive auto vacuum will trigger at that threshold or the storage threshold, and this is modifiable. You can modify this from 400 million to 200 million as well, so that it works like standard. And if you need, and you can even do this as per table level, right? There are parameters in Aurora Postgres on 16 onwards, up to 16 and beyond. And for Postgres as well, now for standard Postgres, there are parameters from 17 onwards, which are called multi-exact offset buffers and multi-exact member buffers. And what these parameters define is how many buffers in the shared buffers, the number is set for multi-exact SLRUs. So basically, the unit is 8K, just like, imagine, just like shared buffers. The unit is 8K, but with these parameters, you are specifying that I need these many buffers for my multi-exacts in the memory. So it can, yes, you can increase these parameters to cache more multi-exact data, reducing the disk IO, but it doesn't really solve the problem, because if you are using a lot of multi-exacts, I would recommend following the other approaches first, like detecting how they are used, maybe changing the application behavior, maybe changing how it's working, and then deciding to increase or tune these parameters. So it's just like not looking at the problem at that time and just delaying it for further. But I would recommend that tune these parameters after following the other approaches, after detecting where the problem is. Reduce long-running transactions is always recommended, because long-running transactions hold or hinder vacuum even for normal transaction IDs. So if there are long-running idle transactions, you basically cannot clean, or you cannot clean any data before this, because vacuum thinks that it's, vacuum knows that it's still visible to an open transaction. So reduce long-running open transactions, and you can use either the idle and transaction session timeout parameter, or you could use any collection poolers which have those settings to not have long-running open transactions. And in summary, multi-exacts represent multiple transactions locking the same rows concurrently. It does happen with operations like these, select for key share or sub-transaction or save points. So if you are using any of these, you can land up in this transaction ID wraparound for multi-exacts. It is a 32-bit counter, so the wrap limit is still 2.1 billion with a storage metric as well for wraparound. Vacuum freeze works for both standard and multi-exacts, and avoid long-running transactions. And the last part is upgrade to Postgres 17 for optimal use of SLRU buffers. And just not that, new versions of Postgres have many optimizations, not just for SLRU, but for other areas of Postgres as well. So it's always a good idea to plan an upgrade strategy. These are some of the useful links. There is a blog which on the same topic, which I've written to, which explains how multi-exact works and almost everything which we have discussed today. So it explains that. The first link actually is very interesting, because I explored that a couple of months back. And it's, if you have a question about, let's say, how SLRU banks work, right, in Postgres 17, type that question in the deep wiki for Postgres, and it gives you a detailed answer with how it was implemented, with the files it is accessing in the Postgres code, with a great explanation. So if you are learning Postgres or you want to understand some concepts in depth, I highly recommend the first link. The second one is for the blog. And that's about it. Thank you so much. I think I have a lot of time left, but If you like this talk, or even if you didn't like this talk, I would appreciate your feedback on this. But yeah, that's about it. Are there any other questions?
Yeah, we have time for questions. Thank you, Divya.
Yes. Yeah.
Wait, sorry, I got on.
So you mentioned that we have a metric, I guess on RDS and Aurora specifically, but I think I've also noticed on other monitoring systems, we have a metric that will tell us out of the box how long do we have until wraparound for normal transaction IDs.
Yeah.
But we don't often have that for multi-exact. I guess one thing that I just wanted clarification on, is that like a hard technical problem to have that metric because of some fundamental way, or is it just like it's been overlooked and could happen tomorrow? Or
Before answering that question, I need to ask if it's still recording. No, I'm just kidding. No, actually, the thing is that we are trying to get that metric in RDS and Aurora for a long time now. We have been figuring out we are trying even to do more improvements in the sense that right now, a standard transaction ID. So coming back, standard transaction ID wraparounds are more common, right? So we are actually even working in the direction to maybe be able to pinpoint that, okay, this is the database, which is the oldest, and this is where the problem is, right, to the customer. So we are trying to improve that experience. But yeah, I don't think it's a hard technical problem. It's just low on the priority list, I would say. So we are trying to, yeah.
Thank you so much for this talk. Maybe one small question. So if we have multiple replicas of our instance, right? One writer and multiple readers, does in that case this multi-exact working? Like suppose my reader queries select queries are running on the reader instance and others are writer, like other writer queries are writing to the writer instance. So what happened in that case? Like,
I'm not I'm not very sure. I will have to test it probably, but at least for standard vacuum, that will impact it, right? So basically, if you have a query running on the replica, let's say you have a read query running on the replica, a long query, and you have a query running on the writer, which now modifies those rows. Okay, so basically, if after the primary has modified those rows, and if vacuum ran, the snapshot is obsolete on the primary and on the replica, and it will say that sorry, rows have been deleted. The rows you were trying have been removed from the primary, right? And that's why we have the hot standby feedback parameter, which can give feedback from the replica to the primary that, hey, I'm running this query, please don't delete these rows. Correct? So it does, yes, normal vacuum does have an impact on the freezing of transaction IDs, yes, because vacuum can't freeze those. So, but I will have to test it explicitly for multi-exacts. I'm not 100% sure, but probably it should, but I'm not sure.
Because in general, we face sometimes a lot of issues with this. We are using Aurora, right? And yeah, we saw this latencies between, okay, because our writers are updating the records frequently, and we are also, parallelly, we are also fetching those records. And if we are thinking about to use, okay, let's use multi-exact with the select for to the reader instance, and how this behaves for the writer, like.
I think it's not, then your problem is just not related to this. We will have to look at the architecture, like why are you having latencies and how it's working. I don't think it is specifically for this, but we can definitely chat more about our architecture and how to improve, the latency part.
Yeah, thank you so much.
No worries. Any other questions?
Your question related to multi-exacts?
Huh?
Well, I was asking.
Any other questions
related to multi-exact? Yeah.
No, Frank, no. You're not allowed to ask.
Thank you so much for this talk. When I see how it is stored in the block, then it is a variable size. And just thinking what happens if there is no space in the block to add an additional, for example, if I select for share and there is no space in the block to store the transaction ID.
So you mean the directory is maxed out? The size the space
in
limit?
the
Or?
block, in the size where you show where it
Ah.
is stored in the block. It's not a reserved size, so maybe the block is full.
I am sorry, maybe I didn't get the question. That's why I didn't allow you to ask.
I
Go
will
ahead,
ask
go ahead,
it,
go ahead. But I think, is your question related to this? Like, why are we?
Yes, it is
Okay.
because you can have a lot of transactions with a share, only one with exclusive, but a lot with a share, and then it takes space in the block.
No, so this is another array, right? This is a separate structure. So basically what I'm doing is I'm only storing this XID there in the Xmax, and then it's saying, okay, these are the transactions which is accessing this exact row, and these are the transactions with this lock modes. Okay, so basically just because I can't share I can't put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all three here, I can't put an array here. This is a single digit I can. So I basically create another structure with a multi-exact ID, which will now tell me that these are the transactions accessing that data. So that's how it is.
Okay, thanks.
That was not too bad. Any other questions? Yeah, there.
Why do the MultiXact IDs have to be stored on disk? It was written that it has to survive a crash, but all transactions are gone when there was a crash.
Because we need the state, right? I mean, if let's say you are writing some data, right, and or you have the state of some data, and you need to, after a crash, you need to recover to know that state, isn't it? So that's why we need that. So similar to PGExact, right? Normal transaction ID data is also stored on disk. So this also needs to be stored on disk to make sure that, okay, what was the state before the crash, and then after we can have that data. So for persistence reasons and for durability, we need to store it. And obviously for faster access, we have it in memory anyway. And I think there was, yeah.
Yeah, so if, let's say, you have a transaction and I have a transaction.
Yes.
I lock a row for share, it's just my exact. You lock it for share, now it's a multi-exact.
Yeah.
So I lock another row somewhere else for share, now that's just my exact. Then you lock the same row for share, now that's a multi-exact.
Yeah.
Does it make a new multi-exact, or does it reuse the one that you used the first time?
For the row, yes. So for the row, no, because this is one row, right? This is one row, and this is that transaction. So whatever transactions are accessing this row will come here with the state. And for another set of rows, so like this is one row header, right?
Okay. So it couldn't reuse it because another transaction might come along and add to only one of them.
Say it again, please.
So it couldn't use the same multi-exact in both rows because a third transaction might come along and change one but not the other.
Yeah.
Yeah.
Good. So, anything else, or
A question there, or is that?
we are good?
Yeah.
Good.
It sounds like everyone had answers to the question. So,
Great.
thanks a lot.
Okay, I think.
That's what I was asking, if you had a question.
So if I understood, the previous question makes something clear to me. So that means that I have multi-exact ID per row. For every row, I have to have a new ID. So that means they grow much faster. They can grow much faster than original IDs. And that's why you have 400 million and not 200 million.
And also the space.
So it's one ID per row, so that can grow extremely fast.
Yes, correct. Okay. And that's why it's not very, as I said earlier, it's not common to see multi-exact wraparounds. But if you are using things like select for share, or you're using a lot of, you're updating and deleting a lot of data which uses foreign key constraints, it is very common to see this then in those cases. Or if you use safe points. So, I mean, the common reasons which we have seen in RDS and Aurora is usually like even the JDBC driver, just because people use the autosave option with that particular setting which I told earlier. So that is one, and the other one is the foreign key update. So that is those are the two main reasons which we have seen. But yeah, it can grow pretty fast.
Okay, thanks everyone, and thanks, Divya.
Great.
Maybe
Thank
we
you
can
so much.
conclude by saying avoid long-running transactions, right?